Welcome to the Mahatma Gandhi Institute of Technical Education and Research Center. In 2004, a national level institute AMGITA has been started in the field of engineering and technology as per guidelines of All India Council for Technical Education AICTE New Delhi. AMGITA is approved by AICTE New Delhi, Gujarat State and affiliated to Gujarat Technological University Ahmedabad, which is also known as GTU. Our goal is to be an institute of generative ideas so that we remain relevant to our society. The MGTA has always been an organization on move with continuous effort on improving its processes and to maintain its relevance to the Indian science scenario, with adding new programs in its programmatic portfolio. We strongly believe in overall development of students, so for that we provide them a different platform like state level tech fest, project fair, different sports activity, which helps students to teach teamwork and problem solving skills to get physical health benefits, boost self esteem, and reduce pressure and stress for prove their skills in distinct area. Welcome to the virtual class of Power System Transients. Myself, Professor Gaurang Patel from Mahatma Gandhi Institute of Technical Education and Research Center, NAVSARI. In this lecture, we are discussing on the behavior of traveling waves on transmission line. Okay. In last lecture, we have seen that. Just a moment. Okay. In last lecture we have seen that there is in some of the introductory part of the traveling waves, then circuit with distributed constants, then the wave equation, and the concept of reflection and refraction of traveling waves. Okay, so in this so I hope you understood very well what is the concept behind the traveling wave and how it's affected to the transmission line. Then uh, what is the distributed constants as well, and the wave equation that what we described in the last video lecture, and the concept of course the reflection and refraction that was very important regarding to the exam point of view. Okay, and in this video lecture we are focusing on the behavior of traveling waves at line termination. Okay, so at the end of the line, if which kind of position in the end of the line, either it is a open circuited line or either it is a short circuited line, that we will see what is the behavior of traveling waves at the line termination. Okay, so it is having some equations which related to voltage and current, and there is different phenomenon regarding the reflection constant and a refraction constant for voltage and current at the line termination. That how this equation is derived, that we will see in this lecture. Okay, so in last lecture we have seen that what is the refraction and what is the reflection of the traveling wave. That I would like to uh, repeat some of the things for that phenomenon, that is reflection and refraction, before moving towards the behavior of transmission line at the termination. So whenever we know the concept of traveling wave, whenever we switch on the supply, suppose this switch S is on, so initially this inductor is going to be charged with the value of 1.5 Li square, and this capacitor is charged with the value of 1.5 CV square. So that's why it will this power will take a time to reach at the destination because of that inherent phenomenon of inductance and capacitance. And each and every transmission line having a such kind of section, and each section having a such kind of inductance and capacitance. That's why we also consider the parameter as a distributed parameter. And one more thing I would like to explain you, that is refraction and reflection waves. So refraction, that we know that refraction, that is the wave or power that will reach up to the destination or up to the end. And refraction, that is the wave which is reflected back from that particular point. This is the reflected wave, you can see. This is the reflected wave which is not going to be at the destination as per the expectations. Okay, so obviously that is the refraction is equal to what? Refraction is equal to the total magnitude of incidence wave and the refraction wave that we already gone through in last video lecture session, that is marked as a video lecture 4. So if you have any query or doubt regarding the refraction and reflection, you definitely refer that video. Okay, so in this video lecture, I'm going to emphasize the things, the equations at the termination of the transmission line when it is open circuited and when it is short circuited. Okay, so here we are considering one transmission line, that is the source, that is the switch S, and when we consider this transmission line as an open circuited transmission line, positive and negative, that is the voltage source that we consider. Okay, so now when we see that when switch S, this switch S is closed, at the time when the switch S is closed, initially that inductor L and capacitor C is going to be charged with its certain values. Okay, so what will be the voltage value of voltage and current at the time of when switch S is on and the line is going to be, this is the open circuited transmission line, and we are interested to find the equation of voltage and current when the line is open circuited. Okay, now if we consider one open-ended line, in that when we close the switch, voltage and current travel through it and reach at the end. That voltage and current is travel through it and reach at the end, but some of them is reflected and some of them is refracted. That what we already discussed, that two phenomena are there. Okay, now suppose we want to calculate those parameters like incidence wave, reflected wave, etc. Okay, some of the parameters that like if that what we discussed, that is the incidence wave, refracted wave and reflected wave. Okay, so if we want to calculate those parameters, then what should be the procedure? That procedure should be known to us, because ultimately we are focusing, or we are trying to know what are the values of that incidence wave, what are the values of refracted wave, what amount of the wave is reflected back at from the particular point. Okay, then at that time we have to follow this procedure. Okay, and this procedure that I would like to explain you over here. So then we follow the procedure. We have to decide one element called dx, which was located at the end of the transmission line. Okay, so one element dx, suppose the element dx, that is I consider, which is located at the end of the transmission line. Okay, so at this time So whatever the changes happen in impedance or reflected wave, or what would be the incidence wave value, etc., at the end we have to find out those changes. Okay, so once when we switch, when we close this switch as, then these parameters are come into the picture. Okay, and what are the values that we must have to the find out or calculate it. From that we can able to understand, or we can able to know what are the values of it. Okay, so the main, if we consider when switch S is on, that is, we know that we have two equations, that inductor is charged with 1.5 Li square, and capacitor is charged with 1.5 CV square. Okay, so once again I would like to say that when you uh, on the switch, or when you give the supply to the transmission line, there is a two energy will be there. Okay, due to the inductance and due to the capacitance, there is a two energy will be there, two kind of energy. One is the electromagnetic energy, and second one, that is the electrostatic energy. So in part of that electromagnetic energy, there is a inductor, inherent inductance capacity will be there. So before that it is charged that with the value of 1.5 Li square. Okay, but right now, to find out those parameters, we are considering the value dx at the end of the transmission line. So it will be included over here, definitely it will be included over here in this equation. So it is, instead of 1.5 Li square, now it's become 1.5 L dx I square. Okay, and similarly it's happened with the electrostatic energy. Instead of 1.5 CV square, it becomes the 1.5 C dx V square. Okay, now this transmission line is open circuited. Okay, so at the time transmission line is open circuited, so our is inductor is are open circuited, and capacitor we are considering as a short circuited. So when open circuited line, inductor is we consider open circuited, so the value of current, that is I, which it is become to 0. Okay, due to the open circuited line. And at this time, when value of current I is equal to 0, the total electromagnetic energy, this is very important term, students, please try to understand. When open-ended line is there, so the value of current will be the 0. So this value of current will be the 0, so total electromagnetic energy is going to be transmitted to the electrostatic energy. Okay, and how these effects will be going on, I will explain you with a relative figure as well. Okay, so now if we are interested to equalize those values, what kind of values we will be get, that is 1.5 LDXI square, which is transferred to the 1.5 C dx V square. If we equalize these values, we can consider that is under root of L by CZ. Okay, how it will be happen, I will show you, just a moment. So here you can see, if you want to equalize those two terms, you will be get, okay, so you will be get this ratio of V by E is equal to root of LC, and we know that root of LC, that is nothing but the impedance at the line. Okay, so if this item is come over here, so V is equal to, it happens V is equal to IZ. And now there is a open-ended transmission line, and we have seen that value of current, that is equal to 0. So the electromagnetic energy which is transferred to the electrostatic energy, so now this V is become 2V. So the value of V, the potential or the value of voltage or value of potential is increased in case of open-ended line. So where initially when at the incidence the value incidence voltage is V, then at the end it becomes the 2V. How it will be happen, I will show you. Okay, because we know that, just a moment. Okay, I hope up till now you just clear all those things. Okay, because what we have the condition, that is refracted refracted wave is equal to incident plus reflected wave. So the how value of V is become to V, that we will see with the help of this diagram. Okay, so over here you can see there is the incidence voltage V over here. That is the incidence voltage V. Okay, so this voltage V is traveled up to the end. Okay, this voltage V is traveled up to the end, and then it is reflected back. But at the same time, we seen that at open-ended line, that is electromagnetic energy is converted to the electrostatic energy. Okay, understand what I want to say? Okay, this incidence voltage is traveling towards the end and it is going to be reflected back. Okay, but due to the open-ended line, the value of current I is equal to 0, so the EME, that is electromagnetic energy, that is, we know that that is EME, that is converted into the electrostatic energy. So the reflected wave is become 2V. So over here this reflected wave, that is become 2V. So that magnitude is double and it is going to be becomes the 2V. So we can say that here coefficient of reflection is positive because of value of voltage is increased over here. Okay, this coefficient of voltage V, that is positive, and because value of increase. So in case of open-ended line, that incidence voltage, if anybody asks to you, that you can say that coefficient of reflection is positive in the case of open-ended line for the voltage. Okay, now similarly you can see when we are talking about the incidence current. Okay, now incidence current is traveling toward up to the end. Okay, now what happened? Due to the open-ended line, value of current is 0. Over here magnitudes remain same. Keep in mind that magnitudes remain same, but to make a balance we have to consider this sign as a negative. Okay, understand what I want to say? So due to the open-ended line, value of current is 0, so we have to consider this sign as a negative. So over here for the current, coefficient of reflection is -1 for the open-ended line. Okay, so just thoroughly I just want to show you that we are talking about the open-ended transmission line. Okay, we are talking about the open-ended transmission line. So in the case of open-ended transmission line, incidence voltage and incidence current, how it will behave, that you can see over here with this diagram. You can say that in open-ended line the coefficient of reflection is positive, that is +1 for voltage, and coefficient of reflection is negative for the current for the open-ended transmission line. Okay, now if it is clear, then we will move toward the short circuited line, or at the end there will be a short circuited. Okay, so what will be the coefficient over there, we will see. Okay, now once we shorted with the open circuited line, finished with the open circuited line, we'll move toward the short circuited line over here. What is the behavior of voltage and current in the short circuited line? Okay, so here I consider one transmission line which are shorted at that termination, and similarly for what parameter, that dx, that what we consider in the open circuited line, same parameter dx I consider in the short circuited line as well. Okay, so in this case when switch S is closed, same thing is happen as per the open circuited line, that the inductor is charged with the 1.5 Li square, and capacitor is charged with the 1.5 Cv square, but we including this parameter dx, and this line is shorted. So in case of short circuit, we know that value of V is equal to 0. Okay, so over here what happened in previous case, we see that electromagnetic energy is transferred to the electrostatic energy, because the value of I was 0 in that case. Okay, in short circuited line the value of V is 0. So obviously what happened, the electrostatic and static energy is converted into the electromagnetic energy. So ultimately the value of current is become higher over here. Okay, we will see over here. So the electrostatic energy, that is 1.5 CDX V square, and this electromagnetic energy, that is 1.5 LDX I square. Okay, so you can see that due to the voltage V is equal to 0, this electrostatic energy is converted to the electromagnetic energy. So over here this value of current is become higher in case of short circuited line, and in case of open circuited line the value of voltage will be doubled. Okay, so similar phenomenon will be there. Okay, but in this case the coefficient value will be differ, or you can say the coefficient value will be the opposite in case with compared to the open-ended circuited line. Okay, we will see the diagram. So in case of short circuited line, if we consider that due to the voltage is 0, electrostatic energy is transferred to the electromagnetic energy. So what kind of diagram we can draw over here? So that is the voltage, incidence voltage, and this is the incidence current. So you can see this voltage is traveled towards the end, the magnitude as usual does remains same, but when it is going to be reflected, due to the V is equal to 0 in short circuited line, we have to consider this sign as a negative to balance that value. Okay, so in this case this sign will be negative, so the coefficient, so you can see over here, so the coefficient of reflection is equal to -1 in the case of short circuited line for the voltage, and similarly for the coefficient of reflection in the current, that is the positive value. So current is twice. Okay, current is travel to the end, then when it is coming back, it becomes 2I. Okay, because that static energy is converted into the magnetic energy. Okay, so it become 2I, and the coefficient of reflection, that is positive, that is +1. Okay, so in case of open circuited line and in case of short circuited line, I hope you understand how the coefficient of reflection is going to be considered, okay, from this video. Okay, so from that we can see that if the line connected with the cable, okay, so that's the value of V is equal to V into twice Z1 divided by Z1 plus Z2. Okay, I will just show you how it behaves. Okay, so now if we move further and if we consider that I have one transmission line. Okay, so this is, consider this one Z1, that is my transmission line, and it is connected with one cable. Okay, so now if we see, suppose we have one transmission line whose impedance is Z1. We have one transmission line whose impedance is Z1. Okay, and I will terminate this one with one cable and its impedance is Z2. Okay, now student, please keep in mind and concentrate over here, because it is very important thing that I'm going to discuss with you right now with this circuit. Okay, so I have one line connected to a cable. This transmission line I consider as a Z1, and that cable, that is I consider, I will terminate this line with one cable and its impedance is Z2. Okay, that means suppose I have one transmission line, value is Z1, and I will terminate it with one cable whose impedance is Z2. Okay, so then the total value, that is refracted value, that means what we discuss about the refracted value, that is the total incidence value. Okay, whatever the incidence value at the transmission line, and plus the reflected value of that particular voltage and current. Okay, so over here refracted voltage V is equal to V into twice Z1 divided by Z1 plus Z2. Okay, and in this case we can see that, that is Z1 is transmission line impedance and Z2, that is the cable impedance. Okay, Z1 is the transmission line impedance and Z2 is the cable impedance. And if you remember and if you watch the video, previous video of that traveling wave, that is video lecture 4, I will discuss that the value of transmission line over here, consider Z1 value of transmission line, that is considered as a 400 ohm, and the value of cable impedance, that is considered as a 40 ohm. Okay, you can see in that video lecture. So if I put this value in this equation, V into twice Z1 divided by Z1 plus Z2, so what should I will get over here? Okay, just try to put it. Okay, so if we put the value of Z2 and Z1, then we will get over here the value of Z2, that is 40, that is cable impedance, and Z1, that is 400 ohm. So over here if we put this value, V dash is equal to V into 2 into 40, 400 plus 40. So if we deduct this value, we will get V dash is equal to V into 2 by 11. So it is approximate the 20% of that refracted wave. Okay, so we can consider that, so the refracted wave travels in the cable whose magnitude is become approximate 20% of incidence voltage V. Okay, got my point? Whatever the refracted wave, that is the refracted wave that travels in the cable. Okay, that refracted wave which is travel in this cable. Okay, travel in this cable whose magnitude is become approximately 20% of incidence voltage V. That means you can see, if you will not terminate your transmission line with the cable, so all the value, all the magnitude of voltage is going to be reflected towards whatever the equipment that you have connected with the transmission line. Okay, and if you terminate it with the cable, so only 20% of magnitude will be passed through that equipment which we are connected toward to the end of that transmission line. Okay, so that means suppose the lightning is occurred on your transmission line. Suppose that lightning is occurred on your transmission line, and if you terminate your transmission line through cable at the substation, then total value of voltage due to lightning stroke past that substation is only 20%. Okay, as per this calculation, total magnitude of that lightning voltage is passed only for the 20%. So benefit of this, we can protect our equipment which is connected at substation, okay, due to only this small amount of voltage is passed of total voltage. Okay, because of only this small amount of voltage is passed because of this cable connection. Okay, and if you don't connect this cable, the entire wave is refracted to the equipment, which may damage to it. Okay, so uh, as we know that each and every substation there is a transmission line that ending is terminated, that's why it is terminated with the cable due to this advantage. Okay, so I hope you understood very well this phenomenon of traveling wave and what is the behavior of transmission line at the termination, and what will be the coefficient of voltage and current for the particularly open circuited line and the short circuited line. Okay, so finally, as usual, we were gone through the question asked in GTO examination. Okay, so now I hope you able to give the answer in the GTO examination. Okay, previously asked question. It is you can see that it was repeatedly asked. That is, explain reflection and refraction of traveling waves by considering voltage and current waves, and write down the expression for reflection and refraction coefficient and that refraction coefficient. Okay, you can see that it was asked in winter 2019, 18, 17, 16 and 15. So obviously it is very important question at the exam point of view. And another question is asked, that is, explain effect of source impedance on the switching operation of transmission lines when the end of the line is short circuited. Okay, so now I hope you able to understood very well the concept of traveling wave and what are the effects at the termination of the transmission line, and what will be the voltage and current equation when a transmission line is open circuited and when transmission line is short circuited. Okay, thank you very much.